In this video, we're going to discuss how we talk about the concentrations of H+ in solution. In pure water, we have 10 to the minus 7 molar H+, which is a very small amount. But the range of concentrations that our H+ can be is enormous. It can go everywhere from about 1 molar all the way down to 10 to the minus 14 molar. This makes expressing how much H+ is present rather difficult. 0.0000357 molar H+, it's pretty easy to lose track of how many zeros are there. And we could turn it into scientific notation. But even then, this is a lot to write and can change rather significantly. A system that lets us more readily show the concentration of H+, with less to have to write and less opportunity to lose zeros in decimal places, is rather important for acid and base chemistry. This involves the pH system. P, lowercase p, was the symbol for log measurements in the old days. We don't use logs as much anymore, but it still shows up and is very useful here. Logs are good for talking about things that change by orders of magnitude, moving decimal places. In our case, the pH is just the negative log of our H+ concentration, whatever molarity our H+ is. In our example above, that would mean the negative log of 3.57 times 10 to the minus 6 molar. Plug that into our calculator. What we'll find is that the pH, the value that equals 5.447. Rather than write out all the zeros or even the scientific notation, I can just tell you that this solution has a pH of 5.447. That would indicate how much H+ is present. In pure water, remember that our concentration of H+ in pure water is 10 to the minus 7. Well, if we plug that in, negative log of 10 to the minus 7, what we'll find is that equals 7. The log system tells us the exponent value. What exponent would I need to get this value out? So what do I need to the power of 10? Well, negative 5.447, if you actually calculate that, is 3.57 times 10 to the minus 6. This is what the log system's doing for us. It's making it so we don't need the range values. We can just say what the exponent on the 10 would be to make us have that number instead. This means that we change by an entire order of magnitude, but I just change my number by 1. If I'm 10 to the minus 6, then my pH is 6. If I'm 10 to the minus 7, my pH is 7. If I'm 10 to the minus 10, my pH is 10. We can represent the concentrations very quickly with pH values. So what naturally happens with water? Well, we get a range from 14 down to about 0. Right in the middle at 7 is neutral. That's pure water. When your H+ and your H- are equal to each other, you have a pH of 7. Your concentration of H+ ions will be 10 to the minus 7. As you go up, you become more basic. As you go down, you become more acidic. If you have 10 to the minus 3 molar H+, well, that is actually way more than 10 to the minus 7, because it's a negative exponent there. So 10 to the minus 3 would be 0.001, where 10 to the minus 7 is 0.0000001. So the larger our H+ gets, well, when we take the negative log of that, we'll get a pH equal to 3. As you go down in pH number, you actually go up in H+ concentration. As you get a larger pH, you go down in H+ concentration. But it still means the only numbers we have to talk about range between 0 and 14 instead of 1 and 0. That value. pH system is an easier way to keep track of these. There's a few equations that are useful then for this. The first and foremost is that pH is equal to the negative log of your H plus molarity, which lets you go from the molarity of H plus to pH, but simultaneously 10 to the minus pH is equal to your H plus. So if you know the pH, if you read a dipstick or are told it on a bottle, you can use that to find the H plus molarity. So these two equations are very useful in the pH system. Additionally, remember that Kw was equal to your H plus concentration and your OH minus concentration. Well, if we take negative logs of all these things, the pKw is equal to the pH plus the pOH. So this is one of our log relations. A negative log of 10 to the minus 14 is 14 for pure water at room temp. So pKw is 14. 14 must equal my pH plus pOH, which is just the negative log of the OH minus concentration. And so we can create equivalent calculations here. My pOH value is equal to the negative log of my OH minus, and 10 to the negative pOH would give me my OH minus concentration. The example we were using before, our pH was 5.447. So we can actually calculate out what the pOH would be. We would subtract 5.447 from both sides. 8.553 would equal our pOH. Just to double check to see if that works with our equilibrium calculation, I can take that, I can turn it into an OH minus concentration. I can say that 10 to the minus 8.553 should equal my OH minus, which calculates out 2.799 times 10 to the minus 9. Does that work with our Kw value? Well, 10 to the minus 14 is our Kw, but that's the equilibrium constant for our H plus and OH minus concentrations. So if I plug in my H plus times my OH minus, they should equal 10 to the minus 14. Because they are in water and they're in equilibrium, if one is changed, the other must adjust to balance it back out to the equilibrium constant. With our values we've been using, we said that our H plus was 3.57 times 10 to the minus 6. We used that to find our pH. We then used that to find our pOH. Use that to find our OH minus concentration, and if we plug that in, 2.799 times 10 to the minus 9, they ought to equal Kw. So 3.57 times 10 to the minus 6 times 2.799 times 10 to the minus 9. 0.999 times 10 to the minus 14, which is basically 1 times 10 to the minus 14 with a little rounding error. So yes, as our H plus was increased above 10 to the minus 7, our OH minus went down. It got below 10 to the minus 7, down to 10 to the minus 9. So as one value increased, the other decreased, so that they still equaled our equilibrium Kw value. Rather than have to do all these calculations to find the concentrations, conveniently we can simply say that, oh yeah, 14 plus pH must equal the pOH. So as long as we know pH or pOH, we can always find the other piece of info. We always know the other concentration of this water breaking apart equilibrium reaction.